what you need to do. And that's what Cisco had to do a few times. It was not exactly, moral, but it's not wrong. It was the right thing at a time for people that he really need to protect.
I like the Space Nine.
I like the Taylor. I like the Cardassian Taylor. He kind of borderlines between really good and bad. So is the Ferengi.
Yeah.
Yeah. The two brothers.
Yeah.
All right. So are you guys ready? Kind of, maybe. Okay. Okay. I'm gonna pass the roll sheet first. And this time I'll pass from this side. No. And I know we have been using Scratch. Hello. Hello. Okay. All right. Okay. So unless you want to teach the class, let me do it. Okay. I don't mind letting you guys teach a class, because I'm still trying to pocket the pay. They're still paying me the same amount whether I'm teaching the class or not. All right. So let's go ahead and get started. We'll kind of suspend a little bit from Scratch because even though it's a lot of fun, but you can also see from the previous two classes that programming is not that simple. Something that seems easy to do actually takes quite a few steps. Okay, take a lot more steps than you expected. So that means if you want to finish the entire Hangman program, it's going to be quite complicated. And the reason why I'm suspending that program for the time being is not because I don't want to finish that program. I really want to finish that program. But the way it is going right now, without any way to structure the program so it's easier to read, the program will be unreadable in this class. It would just be kind of really difficult to read it. So what we want to do, or what I want to do, is to talk about a way to organize your program so we have the organization method in place first, and then we can go back and finish up that program. Okay? So that's what we're going to do now, is to switch our attention to organization, the organization of a program. So let's switch gear back to cisp300. And at this point, we are going to switch to subroutines. Okay? Topic 9, doesn't seem any more difficult than the other ones. It doesn't have pre and post conditions. So for those of you who do not like proofs and math and stuff like that, it doesn't have any of that. In fact, I would say topic 9 is quite the opposite of pre and post conditions. Instead of being math driven, this is all procedure driven. Can you just repeat the same steps consistently? That's what chapter 9 is about. It's also about the organization of a program. So I will go ahead and start on this particular topic here. As a reminder to myself, what I need to go over, but not really going to follow this in terms of just reading out of my own notes. What we want to do is to talk about subroutines. The subroutines are very interesting because it gives you a way to abstract your program. In other words, you can take a big chunk of code out of the main program, give it a name, and then you just say, oh, I want to do that again. I want to do that again. I want to do that again, without having to copy and paste the code multiple times throughout your program. What is the problem of copying and pasting a big block of code everywhere in your program?
If you need to make a change to a bar of code, now you have to go through each of those instances and change it.
Exactly. If you make a mistake before you make all the copies, all the clones, now all the clones have the same flaws, and now you have to fix all the clones, right? And there's no way you can double check and then all the clones are fixed because the compiler, there's no automatic tool to do that. Okay? Every time you program, if you need to copy and paste, you really have to ask yourselves, is there a better way to do it? Okay? Is there a better way to do it? I used to talk about this topic by first explaining why we want to do it, and then we go into the mechanism. I'm changing that order a little bit now. I'm going to talk about the mechanism itself first, and then we'll go back and talk about how it can be useful when you write programs. Okay? So we're changing the order a little bit, and so for the most part, when we start with this particular topic, it would just be a little bit boring, but you also have to kind of pay attention to how I do it. And everything that I do now is going to be in LibreOffice because I'm going to do a lot of traces at this point. Okay. So we'll begin with the definition of a subroutine. In pseudocode, we could use it any way to define it. Sorry, go ahead.
Just checking you have the recorder on.
The recorder should be on. Let me just make sure it is recording from the right channel, and it is on. Thank you. Thanks for checking. It's like a pre-flight, right? Somebody has to check all the knobs, all the things. That's good. All right. So now I have to remember where I was. Okay, right here. I'm defining a subroutine. A subroutine is basically a chunk of code with a name. That's all it is. Okay. So we'll go ahead and define sub is really just like if or while. It begins the entire structure, and then you can specify the name. So in this case, define sub. We can just call this subroutine F1. Okay, F1 is the name of the subroutine, and all it does inside the subroutine is x gets x plus 1. Okay, and define sub. So now we have defined a single subroutine, and the subroutine has one thing to do, which is incrementing the value of x by 1. That's the definition of a subroutine. Outside of the definition of a subroutine, we'll go ahead and initialize x. So we'll say that x starts with a value of 0, and then we'll say invoke F1, and that's the end of this entire program. With the line numbers, and we'll save the file first. So you might want to remind me to upload today's folder, because I think it will be useful today. So we'll just call this one sub1, because it really doesn't have any particular meaning other than illustrating how to trace a program with subroutines. And here we have a trace, so we'll go ahead and...
What does invoke mean?
Invoke means to start something, to... well, I'm not really a good person to explain that. I'll leave it up to Google. But I can defer to some more authoritative, more trustable source. It's better. To cite or appeal, to call on in prayer. Obviously, this has no religious connotation. So it's like in magic. If you watch Harry Potter, okay,
Yes.
All those spells. When you say the spell's name, you're invoking the spell. You're activating the magic of that spell. So that's invoking. That's invoke here. Okay, is that okay?
Yes.
You can say activate, start, call, invoke. Those are all common words for that. So in this case, we're definitely not calling on a deity or a spirit.
IO is the name of God.
Oh,
Biblical.
biblical, yes. All right, so we're going to trace this program. Now, the trace of this program is going to be a little bit interesting, and you have to kind of pay attention to what I'm doing, okay? In other words, I would not be busy copying everything that I do here, but instead, I'll be busy trying to understand what the steps are and make sure that I understand, okay, this step means to do this step means to do this, and so on. Okay. So we have the usual things. We don't need comments in this case because we don't have any conditions to evaluate. We have line number. We have a single variable x, and those are the only two columns that we need for the time being. Okay, so this program is going to have some really new concepts that we have not encountered before. So we'll start with two columns, and if you listen to me carefully, you know that means there'll be something happening to the columns. The precondition is we don't need to know anything about x because we will initialize x. The first thing about this program that we should remember is, hey, we start with line 4 instead of line 1. That's because you do not start with the definition of a subroutine, at least in this class in pseudocode. You do not start with the definition of a subroutine. You start with the first line that is outside of the definition of a subroutine. Okay? In other words, when you look at define sub F1 and define sub, that's almost like an entry in the dictionary. In other words, I'm simply defining the name F1 refers to the block of code which only consists of line 2 in this case, but I'm not using it yet. Okay, I'm not invoking, I'm not activating that code at this point. So you start with the first line that is outside of the definition of any subroutine. In this case, line 4 is that line. Are we doing okay so far with the starting point of a program or an algorithm that has subroutines? Okay, all right. So line 4 is nothing that is difficult, but line 5 is. Line 5, now without explaining why we are doing this, I'm just going to explain the mechanism itself, and then it will be evident later on in today's class why we have to do this. Okay. Line 5 has two things to do. When we invoke a subroutine, it has two things to do. One, it has to remember where are we going back to. Because when we invoke F1 in this case, we will continue execution in the subroutine that we call F1. But what happens when I'm done with F1? I have to go back to somewhere else. So the first thing you want to do is to remember where it is supposed to go back to, and then you can go to F1, because now, after F1 completes, you can know exactly where to go back to. Okay? So in this case, where do we go back to when F1 is completed? There are only two sensible answers, right? The first sensible answer is line 5. The second sensible answer is post. Which one do you think is the case, is the correct answer?
5.
If you go back to line 5, it's going to invoke again, because it will perform the same operation on line 5. So we really need to say post. In other words, the position you want to go back to is not the line that has to invoke, but the line or the next step. Yep.
So that means then we remember the last line we were at, where we go one past it to the next.
Yep, you continue execution past that invoke.
Gotcha.
Yep. So in this case, we have to allocate a new column. Okay, this is something that we have never done before, is to dynamically allocate a column and say, oh, column C is now in use. We have to use column C for something. Okay, we have never done anything like this before. This is the first time we encounter anything that requires the dynamic allocation, which means, okay, I'm reserving this column for some purpose. In this case, I give it a label called return line number, because that's exactly what I'm trying to remember, is where do we go back to, where do we return to after the subroutine F1 is finished. And then we write the answer here, which is post, okay, because we have to go back to post, quote unquote, go back to post, because that's the end of the execution of the program. This is the first step of invoking. Remember where you have to go back to. The second thing you have to do is now to continue execution in the subroutine. The subroutine starts with line 2. Line 1 really has no meaning other than the label, F1. So we start execution on line 2. Are we doing okay so far? The two steps. First, remember where you have to go back to, then continue execution in the subroutine. Okay? And you will hear this over and over again. It will be very boring, because every time we invoke a subroutine, it has exactly the same steps. Okay. So we go back to line 2. We continue execution on line 2. Line 2, even though it's inside a subroutine, it doesn't do anything different than just adding 1 to x. So x starts with a value of 0. Now it becomes 1. And then we go to line 3. You look at line 3 and go like, I don't think it has any special meaning, because remember, we don't trace end if, we don't trace end while, because those lines are only there to indicate the end of a construct. But in this case, it's not. Okay, in this case, even though it is also used to indicate the end of a construct, it actually has actions associated with it. So end define sub on the end of a subroutine has something special to do. There are two things it has to do. So we have to go to line 3 and say what we have to do here. The first thing it has to do is to look up the last return line number that we have allocated. Okay, the last return line number that is still there is column C here. And it will say, oh, okay, so after F1 is completed, after the subroutine is completed, we have to continue execution at post. And that's the first thing it has to do. The second thing it has to do is also very important. it has to say column C now has no particular use anymore, and I'm going to deallocate it. In this class, when I deallocate, I will just use font effect and then use strike through to indicate that column C is now once again available for the rest of the program to use. Well, there's nothing else because we are now at post, so the program has now finished its execution. Are we doing okay so far? Yep, go ahead.
So if this one had like a 6th line, instead of post, it will go to line number 6.
It will continue on line 6, correct. Which is what the next program is going to illustrate, is to have multiple invokes, and then we see how a column can be reused over and over again. Okay? So once again, there are 4 concepts altogether that we have talked about so far. The first concept is on line 5, when we invoke a subroutine, 2 things to do, and the order is to allocate a new column, which is column C, label it return line number, remember where we're supposed to go back to, and then the second thing is to continue execution on line 2, which is the subroutine that we are invoking. That's for invoking a subroutine or calling a subroutine. When we're at the end of a subroutine, there are also 2 things to do. The first thing is to look up the rightmost return line number. It says post, so we can say that, okay, the next step is post. And then the second thing we have to do is to indicate that column C is no longer in use by striking out the return line number. Okay? A lot of this is just notation, but the concept is the most important part, is that column C is only in use during this portion of the program. Okay? Column C is only in use from this time to this time. It's available before, it's available after. Okay? Are we doing okay so far with this concept? So let's go ahead and save it again. This is our first example. I will save the file again using a different name, which is sub2, because I'm going to just make some minor changes to this program at this point. So as somebody suggested, we'll have a line 6 here. So line 6, let's say I want to give X a big boost. I'll add 10 to it. And then on line 7, I'm going to invoke it again. And this program will start to illustrate the value of subroutines. In other words, the first program talks about the mechanism of a subroutine, but it doesn't really quite explain why do we need subroutines. This one will start to kind of illustrate, start to show the reason, the rationale behind the existence of subroutines. Are we ready to start with this one? Okay. So once again, the precondition is we don't need to know anything about X. The first line we start execution is the first line outside of the definition of a subroutine, which is still line 4, same as last time. X gets initialized to 0. Line 4, same thing. Line 5 is the same thing. We allocate a column, label it return line number. So you don't have to copy all of this stuff here. Just kind of focus on the concept. And then we have to remember which line we're supposed to go back to after this invocation. This part is now different from the last time because this invocation is on line 5. Where should I go when the subroutine is completed? Line 6 in this case. That's why the return line number is now 6 and not post. Then we can continue execution. This is the second step of calling a subroutine. The second step is to continue execution in the subroutine, which is line 2. That part is still the same as last time. We're adding 1 to X. X goes from 0 to 1. And then we go to line 3. We still do the same thing as last time. 2 steps again. 1 is to look up the rightmost return line number. It is line 6. So now we know that we have to continue execution on line 6. And then the second step is to say, oh, once we have utilized the value of this column is no longer useful. So I would use this notation to mean that it is no longer in use. This column is now available again. Now we are on line 6. What does line 6 do? Line 6 is a very typical assignment statement. It's going to add 10 to the value of X. X has a value of 1 at this point. Adding 10 to it will make it 11. Are we doing okay so far? And then we go to line 7. What do you think line 7 should do? The same boring stuff that we talked about earlier, right? 2 steps. We allocate a column. We label it return line number. Which column should we allocate? Which column is available? What is the leftmost available column? It's column C again. Okay? So when you allocate columns, you don't just go, oh, we'll just randomly pick a column. You have to pick the leftmost available column. In this case, it's column C. Right? So we are now reusing column C for this purpose. So column C is once again in use. It is serving the purpose of a return line number. This time, what should I put here as the return line number?
Post.
Post. Very good. You guys are definitely catching on quickly. That's the first step of calling a subroutine. The second step will lead the execution to which line? Line 2, the subroutine that we are calling, which is line 2. Line 2 is going to add 1 to x, so it becomes 12. We go back to line 3. Line 3, once again, has the 2 steps to perform. It will look up the rightmost return line number, which is column C. But this time, the value of the return line number is post, because 6 is now overwritten by post. So now I can say we go to post to continue execution. But we also have to remember that column C is no longer in use after this point by repeating the label, but use a strike out to make sure that we understand that we are deallocating the column at this point. That's the trace of the second program. Are we starting to see a value of a subroutine? What if F1 doesn't have a single line? What if it has 200 lines? Well, if it has 200 lines, that means I just saved myself 200 lines of copying and pasting, because now I can invoke the same 200 lines with only saying invoke F1. Is that making any sense? That's one value of a subroutine, is to save the length of the program, because we now have a mechanism so that we don't need to copy and paste anymore. Okay. Are there any questions about this program before we move on to the next program, which is kind of more interesting in a way? Okay. All right, if there are no questions, I'm going to save this again and save it as a different name. This time I know I can give it a different name. I can say nested invoke. What do you think this program is going to look like? Let's go ahead and change the program a little bit here. And I'll say define sub F2. And define sub F2 is going to do something kind of funky. We'll say, I don't know, x gets x times 2, invoke F1, f gets x gets x, I don't know. We have times 2 already. We have plus 1. Yeah, plus 20. Line 8, and define sub. Line 9 is, we still have to initialize x, x has to start with some value. And then line 10 is invoke F2. Fix the indentation, because otherwise it's a little bit hard to read. And make sure that the indentation is all fixed up, width of column all fixed up, and now we are ready to trace the program. All right, so we go to sheet 2, and we can remove a good chunk of this. Okay, we start from the beginning. The precondition is we still don't need to know anything about x because we are going to initialize it in this program. Which line should I start with?
9.
Line 9, because we have 2 subroutines or 2 subroutine definitions here. From line 1 to line 3 is one, from line 4 to line 8 is the other one. So the first line outside of any subroutine definition is line 9, and it does the same thing as before. All it does is to initialize x to 0. Then we get to line 10. Line 10 is an invoke statement, so that means we have 2 steps to perform. The first step is to allocate a new column. The leftmost unused column in this case is column C. So we say it is a return line number, and it has to return to post. because there's nothing after line 10. Then we continue execution on the first line of the subroutine. So remember, when you invoke a subroutine, you always go to the first line of the subroutine that you're invoking. You never start from the middle of a subroutine. And you guys are thinking, but why would I even think about starting from the middle of a subroutine? Well, we'll see later on in today's class. Okay? All right. So we start with the first line of the subroutine. In this case, it's F2. So which line is the first line of the subroutine F2? Line 5. Very good. So line 5 doesn't do anything too exciting. 0 times 2 is 0. And so we put 0 back into X. Nothing really exciting here. Then we get to line 6. Now we have a little bit of an interesting problem because line 6 is another invoke statement. First of all, we have to remember one thing. There's no problem here. You can invoke another subroutine when you're already in a subroutine. In fact, we'll do exactly the same thing as last time. 2 steps to perform. Allocate a column to remember where to return to. And then step 2 is to continue execution with the subroutine that we're invoking. Remember those 2 steps? So which column should I allocate now? Can I reuse column C? Column C is currently in use, so I cannot use column C. So the leftmost column that is available to me is column D. So I go to column D and say, oh, this is my return line number now. But what do I use to remember? Where should I go back to when F1 is completed?
7.
The invoke is on line 6. It'll be line 7. It makes sense. Okay? So we go back to line 7, and then we continue execution in the subroutine that we're invoking. We're invoking F1 in this case, so we continue execution on line 2. Yes?
So for different types of invokes, we're using separate lines? Or, okay,
This is the same type of invoke, it's a different invoke.
for different invokes, like.
Okay, it's the same mechanism. We allocate the leftmost available column.
Okay.
So because column C is already used, so we have to allocate column D in this case.
Why would you go back to line 2? Why would you go back to line 2?
Because the invoke on line 6 says invoke F1, so that means we have to continue execution in F1, which is line 2. Is that okay? Because invoke means we first have to remember where to go back to, and then we go to the subroutine that we are invoking, using its code. Are we doing okay so far? So we go back to line 2. Line 2 doesn't do anything too exciting. It's adding 1 to X. X goes from 0 to 1. And then line 3 is the end of a subroutine. We do the same thing here. Okay, we use the rightmost return line number. Okay, because we have column C, which is labeled return line number. We have column D, which is also labeled return line number. But we choose the one that is the rightmost one. The rightmost one is column D. So it says go back to line 7. So we say here, go back to line 7. And then we say, oh, there's no need for this column anymore. We have just utilized this column. So we go here, and then we strike it through. And then we indicate column D is now available again. Now we continue execution on line 7. Line 7 says add 20 to X. Okay, that's fine. Column B is going to have 21 at this point. Then we get to line 8. Line 8, once again, is the end of a subroutine. We have to locate the rightmost return line number column. Which one is my rightmost return line number column?
C.
Column C, because column D is now deallocated. We cannot use it anymore. So it is column C at this point. It tells me to go back to post. So I have to say the next step is post. But before we go to post on line 8, we also have to remember that at this point, column C is now deallocated. If I had any more code to execute, they can use column C now. But since I don't have any more code, we just say, well, we are at post, we're done. Are we doing okay so far with nested invokes? In other words, we are invoking a subroutine from inside another subroutine. Did I do? Yeah, go ahead.
It's almost like indenting coming back the other way.
Exactly. Exactly. It is called, this is also called last in, first out. Because when you look at the allocation and the deallocation of the columns, it is following the order of LIFO, last in, first out. Okay? Now, since we're talking about last in, first out, it helps to kind of have a visual, or something that relates to your daily life. What do you think has a last in, first out nature? When you go to Safeway or some supermarket and you wait for your turn at the cashier, is that a last in, first out order? No, that's a first in, first out. I will be pretty pissed if it is last in, first out, right? What do you think has a naturally last in, first out nature in real life? When was the last time you moved or helped somebody move with a U-Haul truck?
Well, an example can be a crowded bus. You're
Crowded
the last
bus?
one to enter
Yep.
or
Mhm.
to a car.
That's last in, first out, even though in most cases you don't want it to be last in, first out. But a U-Haul truck is the same way, okay? So let's say you're packing up a U-Haul truck, and then the first thing you want to go like, okay, I got to remember where I'm going to, and this is the map and instruction to go to the destination. Since I want to make sure it is, on the truck, I'll put it inside the truck first, and then you stack everything up on top of that, okay? And then you realize, oh, where's my map? Where's my instruction? How do you get to it? You have to unload the entire truck first. The last thing that you push onto the truck, which is probably a bicycle, will be the first thing that falls out of the truck first. Right? Last in, first out. Okay? How about your refrigerator? Unfortunately, it is also a last in, first out structure because as you buy more stuff, most people just put more stuff in at the front. So what happened to all the stuff in the back?
It gets forgotten.
I call it a mold garden. Okay, various colors, purple, green, and all that stuff. And that's because it is naturally a last in, first out order, even though we don't want it to be last in, first out in this case. Okay. The only way to get around that problem is to either have two doors, so you put things in through one door, but you take things out from the other door, or have a carousel inside, so you can rotate and turn things. Freezers are even worse because, especially the vertical ones, it gets really hard to dig up the stuff all the way down. All right, so we are done with this topic. Now, believe it or not, I have just completed the discussion of the mechanism of invoking and returning from an invoke. But I can do all sorts of tricks to make it look difficult, even though it's not. Okay, so the next one is another illustration of how things are actually not as difficult as it is, even though it looks difficult. So this time, I'm going to define a subroutine here, and make sure I save the file as a different name first. Because otherwise I'll call this recursive. Okay. How many people have heard of the term recursion or recursive? It has nothing to do with cursing. You're not cursing somebody again. This is really bad joke, right? Huh?
Curse at a recursive system.
Yes. Okay, in what situation did you hear the term recursive or recursion? Star Trek is one. Okay, if you watch the Next Generation, Star Trek: The Next Generation, they will say, oh, data is having a problem. Is a recursive, adaptive algorithm, blah 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 blah, and with my limited knowledge of programming, every single instance they use the term recursive is all wrong. So forget what you learned from Star Trek: The Next Generation when it comes to recursion. It's actually very simple. Okay. All right. So we're going to write a subroutine like this. We'll say if x is greater than 2, greater than 0. We'll make it greater than 0. Then x gets x minus 1. Invoke f1 and if and define sub. And then we say x starts with a particular value. I'll fix the indentation later, so don't worry about that part. We'll make it start with, just so that we make sure this is really boring, we start with 3. And then we say invoke f1. And it's time to fix up everything else. We'll fix indentation. This has to indent twice. Click, click. This has to unindent. This has to unindent. Now we have our third program in subroutine invocation. And then we go to, oh, we don't have the second window. Gonna create it. Go to sheet 2. And we'll go ahead and start. Not from scratch. We'll go ahead and start from scratch here. This one looks really funky, doesn't it? Okay. Not only do we have a invoke inside the subroutine, which we know we can handle, it's invoking the very same subroutine that it's in. Okay? But I promise you that this is exceedingly boring. Okay? You mentioned the word recursion in a programming class other than the one that I teach. It will strike fear in the heart of everybody in the class. It's like, recursion, no, not recursion. Okay? But in this class, you hear the word recursion, you go like, boring. Nothing new, boring. Because it really is no different from what we have talked about before. Okay? So this is the trick. Okay? You will see recursion again and again in all your other programming classes, especially if you're on the track to get your computer science degree. Okay? If you take cisp 430, you will see recursion again. I believe in 400 you might see it again too. Okay? So having a really good handle on what it really means is very important in this class, so that by the time you get to 400 or 430, you look at recursion and go like, yeah, I know exactly what it's supposed to do. No problem. Because it really is a very simple mechanism. Precondition is still unknown in X. We start execution on line 7 in this case because that's the first line that is outside of the definition of any subroutine. And X gets initialized to 3 in this case, not 0. And then we move on to line 8. It's a simple invoke statement. So once again, what do we do when we have an invoke? 2 things to do. Allocate the leftmost available column. What is the leftmost available column?
C.
Column C, very good. I label it return line number. Remember where to go back to? Post. Yep. Typically, it's the line next to the invoke statement, but we'll see later on that sometimes it's not. Okay. And then where do we go? Step 2 of invoke. Go to the subroutine that we are invoking from the beginning. Where is the beginning of sub 1? F1. Line 2, very good. So we now continue execution on line 2. And you know what, I forgot one thing, because this time we do have a condition to evaluate. So we have comments here. Not the conditional statement is the easy part. Okay? Line 2 now has a condition to evaluate. X is greater than 0. X is greater than 0 is X is 3. 3 is greater than 0 is true. Very good. All right. And we can make this column a little smaller. Then where do we go? We go to line 3. When the condition of a conditional statement is true, we execute the then branch, which is line 3 in this case. Line 3 is really simple. We are just decrementing the value of X by 1. So X goes from 3 to 2. No big deal here. Then we go to line 4. Okay, line 4 is the one line that can give a lot of programmers big headache. It's like, what do we do here? Okay, we're invoking the same subroutine that we're in. The answer is, it doesn't matter. You just use this very same mechanism that we have done so many times already today, and we just apply it blindly. Okay, the key word here is to do it blindly. If you do not do it blindly and you try to interpret more than it is, that's why people get into problems, is trying to read more into it than necessary. So here, we just do it blindly. 2 steps when we invoke. Tell me what those 2 steps are. We allocate the leftmost available column. What is that column? Column E. We label it return line number, and then we write down the line number that we are supposed to go back to when the invocation is done. This is when it is a little bit special, because the next line is line 5. But remember, we don't trace line 5. So after the invoke, where are we supposed to go? Line 6. I would use line 6 instead of line 5. And then what is the second step of invoking a subroutine? We continue execution on the first line of the invoked subroutine. Where is that?
2.
Line 2. Yeah, exactly. That's it. Oops, wrong place. That's it. That's the mechanism. Have I changed anything, about how we invoke a subroutine? No, I didn't change a single thing. This was exactly the same thing that we did in the previous 2 or 3 sample programs. 3, exactly. All right, so we get back to line 2, and guess what line 2 is going to do? Same thing that we were doing before. X is greater than 0 is true because x has a value of 2. Then we go to line 3, we decrement the value of x. It goes from 2 to 1. Then we go to line 4 again. And what do we do here? Same boring stuff. We allocate the leftmost available column, which in this case is column F. Label it return line number. And then we remember where do we go back to when this subroutine is done. We don't go back to line 5, so we have to say line 6, which is outside of the conditional statement. And then step 2 of invoking is to continue execution on the first line of the subroutine. First line of the subroutine that we're invoking is F1, which is line 2. Okay? Line 2 is the first line of F1. So we continue execution over there. We ask the same question again. You can see how boring this gets, right? Go to line 3 again. This time it is 0. And we still have to go to line 4 because, after line 3, line 4 is sequence, right? It's a sequence, so you have to go to line 4. And I'm just going to resize the columns a little bit here. On line 4 is an invoke statement. We have to allocate the leftmost available column, which is column G. Label it return line number. We have to go back to line 6. And then continue execution on line 2, which is the first line of the subroutine that we're invoking. The fact that it is the same subroutine that we are from makes no differences whatsoever. So that's what you need to remember is the mechanism is the same. This is the 4th sample program that we have done so far. It makes no difference whether you only have one invoke from outside of a subroutine, whether you have 2 invokes from outside the subroutine, and invoke from within a subroutine but invoking a different subroutine, or an invoke from a subroutine to the same subroutine. It makes absolutely no difference. The mechanism is still the same. So on line 2 this time, x is greater than 0 is false. Then where do we go? Nope. We go all the way to line 6 because we skip over the entire conditional statement, right? Yes? Okay. What do you think line 6 should do? We are at the end of the definition of a subroutine. It has 2 things to do too. One, it has to go to the rightmost return line number to tell it where to go back to. And then it has to deallocate that particular column. So in this case, what is the rightmost return line number column? Column G, okay. And column G tells me to continue execution where? Line 6. It looks kind of weird, but you know what? I'm just going to follow that blindly. So we'll say we'll continue execution on line 6, but remember, we have to deallocate a column once it is used. So we just copy and paste and use strike out to indicate the column is no longer in use. And now we execute line 6 again. Wow. What do we do on line 6? The same boring stuff. Locate the rightmost return line number column and use that to tell you where to continue execution. Which column should we use this time? Column F, because column G is now deallocated. We cannot use column G anymore. So column F is our rightmost return line number column, and it tells me to go back to line 6. All right, fine. I'll just go back to line 6 as instructed. And then that column, once again, is no longer useful, so I deallocate it. Now we are on, guess what? Line 6 again. So we do the same boring stuff again. We locate the rightmost return line number, which is column E in this case. It tells me to continue execution on line 6. And then the second step is to deallocate the column that I just made use of. Now we're back on line 6. And then we do it one more time, right? Locate the rightmost return line number. In this case, it's column D. This time it tells me to continue execution at post. But once I make use of that column, I say, well, it's not useful anymore, deallocate it. And then we continue execution at post, which means, hey, we're done. Yep.
So why do you go like where it says 2, 3, 4 the first time? So why do you pick the return line to 6?
Because there's no line 5, we don't execute line 5. Line 5 has no meaning. So the actual next step after the invoke is line 6. When you look at the conditional statement here, if this, after this invoke, there's nothing to do after the invoke inside the conditional statement. So the natural next step is actually line 6. Is that okay?
Yeah.
All right. And that's recursion. Is it really hard? It's not hard when you just focus on the mechanism itself and not. When I learned recursion, I had problems understanding recursion in my Pascal class, because when I took programming classes, we program in Pascal and not pseudocode. But because there's no trace like this, and there was no explanation of what actually happens when you invoke a subroutine, I just could not understand how it works for the for the rest of that semester. Until I took assembly language programming, then I can visualize everything and go, oh, so that's how recursion was done. But when I teach this class, I'm teaching the mechanism also, so that you guys can focus on the mechanism and not get kind of hung up with the source code itself. In other words, if you have to trace the program, but without this, then it becomes harder. Because it's hard to keep track of where I am supposed to go back to anymore. But with this part, it's not as hard. Are we doing okay so far with this? Okay. So what we want to do next is to use recursion and try to implement a very common function, or a common type of calculation that we call factorial. Okay. Can anyone remind me what is factorial? Okay, factorial. Okay, let's start with some concrete examples. 4 factorial, which is also denoted as 4 exclamation point, is what? 4 times 3 times 2 times 1. Okay, nothing more boring than that, right? Which in this case is 24. Okay. How about 5 factorial? I just want to bore you guys a lot today. Yeah. What is 5 factorial? 5 times 4 times, whoops, I cannot type. 5 times 4 times 3 times 2 times 1, which is 120. I could have asked you what is 6 factorial or 7 factorial, but I think that's enough, okay, right? Okay, but there's something special about factorial. Because when you look at 5 factorial, do you see 4 factorial in it?
Yes.
Yeah, that looks kind of like 4 factorial, because I could say that 5 factorial is 5 times 4 factorial, because 4 times 3 times 2 times 1 is 4 factorial. Now, if I tell you, so how about 4 factorial? I can probably say as 4 times 3 factorial, right? Because 3 factorial is 3 times 2 times 1. Are we seeing a kind of strange nature of factorial here? Okay, if I give you n factorial, in general, you can say n factorial is the factorial of n minus 1, unless n is 0. Okay, if n is 0, 0 factorial by definition is 1. Are we doing okay so far? So that means if I want to use a funky way to define factorial, I can say, n factorial is defined as follows. If n equals to 0, then n factorial is by definition 1. Else, n factorial is n minus 1 factorial times n. Okay? Is that okay? Can everybody understand that notation? Sorry?
How can we get 0 factorial equals 1?
0 factorial equals 1 is by definition. It's like an axiom. 0 factorial is 1.
So 1 factorial is also 1.
1 factorial is also 1. But that's only because it is 1 times 0 factorial, and 0 factorial is 1.
Okay, so that makes sense.
It makes sense, huh? Okay, but why do we want to bother with factorial other than testing your calculator and see how big of a value it can handle? Why is factorial so important in computer science? Because in this class, we're not going to talk too much about it, but it is important. It's because factorial gives you the number of, I cannot remember, it's permutations or combination. Which one is order independent or order dependent? Combination is the one that is order dependent, right? Okay, before I make a mistake and have all the math professors make fun of me, I'll take a look at combination and permutation, because that's the other one. I think we'll talk about permutation is when the order is important. Combination is when it is not important. The combination to the save was this, okay. So in mathematics, when the order is important, it's permutation. Okay, so it is permutation. All right, so we get back to our notes here. Okay, so factorial has to do with the number of permutations. Okay, in other words, let me try to use an example here. Okay, remember the traveling salesman problem. We touched on that a little bit. Remember the pizza boy, who has to deliver pizzas, and we want to optimize the path. Okay, so let's say the pizza boy has. Okay, instead of using the whiteboard, I'll just use my trusty notepad here. Okay, let's say we have 4 destinations: A, B, C. Well, let's only pick 3 because 4 is going to be a little bit too much. So we have A, B, C here. Okay, so those are the 3 places where I have to where I have to go. How many ways can I traverse A, B, and C? If I limit myself to only go to, I cannot revisit a place twice, and each place has to be visited at least exactly once. 6 ways. Now, how do we know there are 6 ways? Because there are 3 ways to pick the first one, 2 ways to pick the second one, and only 1 remaining way to pick the third one. But if I want to spell it out, I can do it like A, C, B. And then we have exhausted everything for A as a beginning. So we can start with B, A, C, B, C, A. And then we start with C, B, C, A, B, and then C, B, A. Those are the only 6 possible permutations in this case because the order is important. Okay? And that's the reason why there are exactly 6 is because I only have 3 choices to choose the first destination. But once I pick the first destination, I only have 2 remaining places to visit. So my second one only has 2 choices. And then the third one, is only 1 because there's only 1 last place to go to. Is that making any sense? So if I have 4 places to go to, then I have 4 choices for the first stop, 3 choices for the second stop, 2 choices for the third stop, and 1 choice for the last stop. So that becomes 4 times 3 times 2 times 1. That's permutation. So we have 24 permutations when we have 4 destinations. Is that making any sense? Now why? No. Okay, fine. That's is that really useful? It's useful if you want to decide, should I buy Lotto today?
Oh.
What? Lotto and Factorial? They are related? They are. Okay? Okay. Tell me about Lotto. Well, instead of telling me about Lotto, we can go to their website for the definitive, definition of Lotto. So we go to California Lotto, which is supposed to help education. Okay. So we'll go to pick a particular game. How many Lottos do we have? A lot. Okay, so we'll just pick, superlotto plus. Okay, fine. And where are the rules? I know it is required by law that they have to spell out the rules.
How to play?
Hmm?
Isn't it how to play?
How to play, okay. Okay, find a superlotto plus retailer. Okay, fine, that's me. Pick 5 lucky numbers from 1 to 47 and 1 mega number from 1 to 27 on the superlotto plus play slip. Okay, so we pick 5 numbers from 1 to 47. Is that a permutation or is it a combination? It's a combination, okay? It's a combination in this case, which means the order is not important. Great. So how do we know how many combinations do we have? Well, it's actually a lot easier than you think it is. Okay. All right. So out of 47 numbers, how many choices do I have for the first choice? Let's say it is permutation. Okay. We'll figure out the combination later. We'll figure out the permutations first. So let's say the order is important. How many choices do I have for the first number? 47 exactly, right? For the second choice? 46, 45, 44, 1, 2, 3, 4, 5. Okay. So this is the number of permutations that we have. But remember, in Lotto, the order is not important. It's not important. Okay. So the next thing you have to say is, okay, let's say I pick 5 numbers. Okay, you have A, B, C, D, E. Out of these 5 numbers, how many permutations can I get out of 5 numbers? Do we know that number? Do we know that answer? Out of 5 things, how many permutations can we get out of 5 things? 5 times 4 times 3 times 2 times 1, right? Yep. Okay, so that means one combination in this particular case has 5 factorial permutations corresponding. Is that making any sense? Only for this case, okay? Only when we are dealing with this specific problem. But does it make sense in this case? Okay, I pick out 5 numbers, okay? There are 5 factorial permutations, and this is the number of permutations to each combination. So if I want to figure out how many combinations we have with picking numbers out of 47, what do you think I have to do with this number? That gives me the number of combinations when I have to pick 5 numbers out of 47. Is that okay? Making any sense? Yep.
My question is, can you pick the same numbers?
No, you cannot. In Lotto, you cannot pick the same number because they actually draw the ball out of the cage.
Oh.
So you cannot pick the same number. Yep.
So it's basically 47 factorial divided by 5 factorial?
Not quite. Not
Right.
quite. You're getting close. Yep.
So what would that number give you?
This number? It's some really huge number.
What does it mean, like your chances?
It means, well, we're not quite done yet. It means there are this many combinations out there without even adding the mega number. Okay? Now, does anyone know whether the mega number has to be different from the other 5 numbers, or can it be
No,
the same?
it can be the same number.
Can be the same?
Different
Okay.
set of balls.
So the total number of combinations would be 27 times this, because this is just for the 5 numbers that you pick. And then on top of that number, in order to win the mega, you also have 1/27th of a chance to actually get it. Is that making any sense? Okay. Now, but this doesn't look like factorial to me, Tag. You have a problem here. This is not factorial. Well, excuse me. Right? It cancels out. Because this part here is really 42 factorial. So if I know how to find 47 factorial, I can divide 47 factorial by 42 factorial, so it becomes the number of permutations. With the number of permutations, I divide it by 5 factorial to get the number of combinations. And then with all the combinations, we still have to multiply that whole thing by 27, because 27 is outside, is independent to the 5 numbers that I have just picked. So this is the total number of possible lotto tickets. Okay, or configurations. Okay, I know you can buy 2 tickets of exactly the same combination, of exactly the same configuration, but this is the number of configurations out there.
Unique lotto ticket numbers.
Right, because well, you can have 2 lotto tickets of exactly the same configuration, so both people will win in that case. So let's try to figure out what that number is. It's already kind of big. I'm not sure whether my calculator can do this. Let's give it a try. BC, 5 factorial. Nope, doesn't understand factorial. Okay. Let's see, what should I do here? Calculator or spreadsheet? Spreadsheet. Okay, so we'll just go ahead and use factorial. Okay, doesn't know factorial, fact. Okay, so we are talking about 47 factorial divided by 42 factorial divided by 5 factorial, and then whatever it is remaining, multiply that by 27. So this is the number of possible configurations. It's I'm really bad with counting, 41 million something, I think.
402,353 combinations.
Yep, so you have 1 over 40 million of that's your chance of your ticket matching the actual configuration, matching the exact number. 1 out of 40 million. Okay, but that makes the calculation so easy, right? I mean, if the prize money is $40 million, or let's say $42 million, then it's worth it, because I have on the average a chance to win my $1 back, so I'm not losing anymore. Well, excuse me, the state wants your money too. Okay, if you get $40 million as a lump sum, can you imagine how much you have to pay as taxes? Because you have an income of $40 million. The state of California is going to say, thank you very much, here's a big chunk gone. Okay, is it close to half? About half? Okay, so if you win $40 million, you only get $20 million that you get to keep. And then guess what? When the prize money is that high, there will be a lot of people buying a lot of tickets. So you might have another person who has exactly the same number, and you have to split your money with that person. Okay, so you really need your prize money to be a lot more than 40 million to make it break even. Or you can just say, yeah, forget all statistics and what tech has to say. I just feel lucky today. That's also another mentality.
20 million is better than no million.
Well, a lot of people think, I'm just losing $1, but I have a chance of winning all that money, right? But the chance is has never been on your side, right? Because if chance has ever been on your side, what is the whole point of lotto? Is that making any sense? Is that kind of explaining why factorial is kind of important? When you take classes in statistics and also probability, you will see factorial again and again and again and again. The number of combinations again and again and again and again. Because when you have polynomials, the number of combinations of the different factors, that also has to do with the number of combinations. All right. Okay, now that we have found a common use of factorial, we'll go back and talk about factorial a little bit and explain factorial has a recursive nature. That's the bottom line, okay? So even though we have just illustrated the importance of factorial, I want to go back to factorial and say, but factorial has a recursive nature. In other words, factorial can be defined using factorial itself. That's a recursive definition. Now we find a lot of stuff in real life that has a recursive nature. You look at the tree, okay? You look at the tree, what do you get out of the main trunk of a tree?
Branches.
Branches. You follow that branch, what do you see at the end of that branch? More branches, just smaller, right? You follow that branch, smaller branch, what do you see at the end of that branch? Okay, let's say you see a leaf, okay? You follow the main stem of a leaf, what do you see? More branches. So nature has its own way of having recursive nature in itself as well. Okay? All right. So now that we know recursion is important and factorial is important, we'll go ahead and write a very clumsy way of doing recursion using the mechanism that we already have. So we'll go ahead and write the algorithm. We'll go ahead and trace it. I think we have time to trace it at least once. So we'll go ahead and say new spreadsheet. Where is it? No, that's not it. Okay, close, close. Oh, that's it. Okay. All right. So we'll say define factorial. Okay. And we'll say if n is greater than 0, then we want to do the recursion, which means n gets n minus 1, invoke factorial. When it comes back, I know that what the result of the factorial is up to this point, so I need to, I cannot do that just yet. Trying to decide what to do here. Okay. We can say n gets n plus 1, and then the result is the result times n, and if else r gets 1, and if, oops, that cannot be, and if here, row, and define sub, and we initialize n to be, let's say 3, okay? We say invoke factorial. How many people want me to fix the indentation? Well, that really helps to show the importance of indentation, because without the indentation, I can still read the program. It's just a lot harder. Okay, so we'll fix these guys and this guy. Is that better? Sometimes, the best way to explain why something is important is not to do it. That sounds kind of zen, right? All right, so let's go ahead and trace this program. We have enough time to do it. And trust me, it's going to be quite boring. All right. So we have line number, we have comments, because we do have one condition to evaluate. And then we have two variables. We have n and r. And then we have to dynamically allocate more stuff later on, but we'll do it as we get to those points. The precondition is we don't need to know anything about n or r. Okay, so this one looks kind of funny because how can we do this without knowing r to begin with? Well, actually we don't. All right, so we start with which line? The first line outside of the definition of a subroutine is line 11. Okay, line 11 has a very simple job to do. N gets initialized to 3. We move on to line 12. Line 12 is the invocation of a subroutine. Two things to do. Allocate the return line number column. Remember where we're supposed to go back to. This time is post because there's nothing after line 12. And then we continue execution on the first line of the subroutine, which is line 2. Line 2 has a simple condition to evaluate. N is greater than 2. N is greater than 0 is true, right? Then we go to line 3. Line 3 says we decrement the value of n. N goes from 3 to 2. Line 4 is going to invoke a subroutine. Same thing, we allocate a new column. We allocate the leftmost available column, which is column F in this case. We remember which line we're supposed to go back to after line 4. Fortunately, this time we have a line 5 to go back to, so we just write line 5 here. And then we continue execution in the subroutine that we are invoking on the very first line. So that's line 2 again. N is greater than 0 is true because 2 is greater than 0. So we follow the same steps. We go to line 3, we decrement the value of n by 1. It goes to 1. And we go to line 4, which is an invocation. We allocate the leftmost available column, which is column G, label it return line number, and remember where we have to go back to, which is line 5. And I'm just going to shrink this a little bit because we need a little bit more than that. Then we continue execution in the subroutine, starting with the first line in the subroutine, which is line 2. N is greater than 0 is true. Go to line 3. We decrement n to 0. We go to line 4, which is an invocation. Do the same thing. Allocate the leftmost available column. Label it return line number. And the return line is line 5 because the invocation is on line 4. Then we continue execution for the last time in the invoked subroutine, which is on line 2. N is greater than 0 is no longer true. It is now false because n is 0. So we go to the else branch, which is on line 8. Line 8 says, R gets 1. Fine, R gets 1. Then we go out of the conditional statement. We continue on line 10. Line 10 is the end of a subroutine. We have to do the quote-unquote return action, which has 2 steps. The first step is to look up the rightmost return line number column, which is column H. Column H says go back to line 5, so that's where we'll go back to. But we also have to remember that column H is now no longer in use. We have to deallocate it. So we go to format cells, change it to strike through, just to indicate this column is no longer in use. And then we continue execution on line 5. Line 5 says add 1 to n. N goes from 0 back to 1. Then we go to line 6. Line 6 says R is R times n. N is now 1, R is 1. So the new value is still 1 because 1 times 1 is 1. After line 6, we get out of the conditional statement. We go to line 10. Line 10 is at the end of a subroutine. We repeat those steps that we did earlier. The rightmost return line number is now column G. Column G tells me to continue execution on line 5. That's where we'll go. And then we know that we do not need column G anymore. It is now deallocated. And now we run out of space on the screen. And I have a trick to do it. I can do this trick here. And it's really handy. It comes in really handy. Just like that. So now I can scroll the 2 windows separately. See how nice it is? Now we get back to on the line 5. Line 5, is going to do the same thing here. N gets n plus 1, so n is now n has a value of 2. Line 6 wants to compute the product of R and n. R has a value of 1, n has a value of 2. 1 times 2 is 2, so R now gets a value of 2. After line 6, we get out of the conditional statement. We continue at the end of the subroutine, which is on line 10. At the end of a subroutine, we do the same thing. Are you guys getting bored? You should be. You should be getting bored by now. Okay, so we go to line 10. It does the same thing. It goes to the rightmost return line number column, which is column F now. It tells me to continue execution on line 5. Now that column has to be deallocated. Okay, now we're back onto line 5. Line 5 adds 1 to n. N goes from 2 back to 3. We go to line 6. Line 6 wants to compute the product of R and n. 2 times 3 is 6. It stored the 6 back into R. So column D is now 6. Then we get out of the conditional statement. We continue on to line 10. Line 10 is the end of a subroutine. We locate the rightmost return line number, which tells me to go back to post. And then we say, oh, we have no use of that column E anymore. Deallocate it, continue execution at post, and we are done. 6 is the factorial of 3. And it took me all 5 minutes. But it is factorial, okay? It is factorial. And you will see, I'm using factorial as an example because as we add more concepts to subroutines like local variables and parameters, we'll refine this algorithm until it looks really clean. This is really dirty, okay? It's really dirty, but we'll clean it up as we introduce additional concepts. Are there any questions about the concepts that we have talked about today? It might be helpful to kind of go through the recording again, because a lot of this stuff is action, right? You do this step and then do this step. So the more you get used to the steps, the better it becomes. I think a homework assignment may be helpful too, so that you guys can go through the same process. So I'll create a homework assignment for subroutines, just simple stuff, like this one, and then we'll talk about parameters next time. So you might want to read ahead of me in terms of local variables and parameters will be the next topics. So try to read ahead of me, because these concepts all stack up on each other. All right, I'll see you guys on Thursday. Happy Halloween. I'll see you guys later, and don't get too much candy. Unless you have a good dental plan.
Yeah.